All right, so now we're going to start on clouds and pressure. So clouds are just tiny droplets of liquid and or small ice crystals suspended in air. Three things are needed for any type of cloud to form. The first off is there has to be some type of moisture or water in the air. And then you have to have the presence of condensation. That means we're going from water vapor to liquid water. It's got to go back from the gas phase to the liquid phase. And to do that, you need a condensation nuclei, something for it to latch onto, to condense onto. And then another one is you need cooling temperatures, which is one of the reasons why we were looking at dew point temperatures, which tell us, the probability or most likely that there's going to be rain because of clouds forming. All right, so condensation nuclei, what are those? Those are any aerosol or airborne particles in the atmosphere which provide a surface for water molecules to condensate onto or condense onto. Some types of condensation nuclei that we can find are ash from volcanoes. So that there's so much of it and it's such a small particle that it goes throughout the whole atmosphere all over the world, and it can definitely help form clouds because of it. Dust from dust storms, sandstorms, that from desert winds can form a sort of molecule that it can condense onto. Then you have salt crystals from over salty water, like the oceans. And then last but not least, chemicals in the air. That's like any of the pollution that you see out, carbon dioxide and stuff like that. Condensation nuclei can form onto it. Any little bit, any little particle it can form onto. And then we have this thing called adiabatic cooling, which also helps to form clouds, which then form rain. And the cycle goes on and on and on. So what is adiabatic cooling? Well, as air rises, because it's under less pressure, less dense, it's not as compact anymore. It starts to expand as it rises. And as it expands, as it rises, it cools. And once it hits that dew point temperature, all that water vapor will start to condense back onto the condensation nuclei, forming clouds. And then once it gets high enough and cool enough, and all that water vapor has condensed, and then it can start to rain or snow or sleet or something like that. So this whole process is called adiabatic cooling. And with the right conditions, you can reverse that and have it adiabatic heating. So going back down instead of going up. So as it heats, it condenses or compacts, and it becomes warmer, and less warmth. Or sorry, more warmth. Okay, so there are different types of clouds and different types of areas in our troposphere to stratosphere. Like the stuff up here is more stratosphere. Stuff down here is more troposphere, where most of the water vapor is. And so as we can see, we can start out with the lowest level. Those are when you have the stratus clouds. You have stratus, stratocumulus, and cumulus. And then as we go up, those are the low clouds, the ones that kind of float underneath and they look like they're moving. It's really, really cool if you look out and you watch the different clouds. You'll have upper layer and then lower layers, and they move at different speeds. And then you have the middle clouds, where you have the alto cumulus, the altostratus, and then the cumulonimbus, which if you've ever watched Up, this is what Kevin says, or not Kevin, Kyle. Oh goodness, I forgot his name. The kid says to the older gentleman, saying, "Hey, look, there's cumulonimbus." And then at the very, very highest point of where the water vapor goes, you have the high clouds. Those are typically in the lower stratosphere. You got the cirrocumulus, or the mackerel sky. That kind of is in the movie Planes, where in the first one where they say, hey, if you get up there, the wind goes really, really fast. You can go really, really fast. Then you have the cirrostratus. That's when it almost looks hazy-ish out with a halo around the sun. It's kind of very, very light. The cirrus kind of just looks like wisps. And then when you have this huge cumulonimbus, you'll have an anvil top up there. All right. So if conditions are right, adiabatic cooling and the cloud formation, it can produce very, very rapidly. And adiabatic cooling, remember, is when you have the warmer clouds, which are tightly compacted. As they rise, they cool, and then the water vapor starts to condense, and it forms clouds. Now, if this happens really, really, really fast, we get this. The cloud formation, very, very rapid. It can make thunderstorms. In some instances, these storms can grow in intensity and flow to produce deadly tornadoes. Now, we don't get so many. We get maybe one or two a year. But if you're in like Tennessee, and there is Tornado Alley, if you're in there, they get them a lot. And a lot of those anvil clouds that we saw on the last slide are like this, where you'll see there's the tornado, there's heavy precipitation that could go from anywhere from rain to hail, like huge, like golf ball, softball size hail. And you can see this is kind of like the schematic diagram of a thunderstorm, like a really, really severe one. All right. And then we're going to go into air pressure, just a little bit. Air pressure. So air has weight. It does. And because it has weight, it causes pressure or creates pressure. The force of gravity that pulls on us causes that air to have weight. And we can take this air as like being at the bottom of a pool, where the pool is the actual air in the atmosphere. So if you look at this, the atmosphere gets pulled in because of that gravity. And it acts equally in all directions. Gravity acts equally all directions within objects containing air, like buildings, empty human bodies, empty bottles. So like right here, my bottle, right here, it has air pressure on the inside. It's equally. Even empty bottles, just to keep their shape, they have pressure. Now, if I was to take all the pressure out of that, it would implode, right? But here's the thing, the actual air pressure at sea level, and we go by sea level, is about 14.7 pounds per square inch, right? Things to measure air, we already saw one of them, which looks like this. We're going to start looking at those. So one of the things you got to know is air pressure is dependent on altitude. If you look at page 14 of your reference table, you'll see that the pressure does change as you go up in our atmosphere. And the higher you go, the less atmosphere is around you, so there's going to be less pressure. The closer you are to Earth, the more pressure you're going to have. As you go down farther in Earth, there's going to be even more pressure. If you look at page 10, you will see the pressure. Okay, so one of the things we measure pressure in is barometers. And it comes in hundreds of variations, but in two basic designs. So the first we have is a mercury barometer. I don't have one of those. Legally, I can't have one of those. They look very similar to this. And then an aneroid barometer, which I've shown previously, that looks like this. So the first one we're going to look at is the mercury barometer. It is basically an inverted tube that has mercury in it and a little tray of mercury also. So there are some with water in it. So you fill the liquid into the tube inverted upside down in a pan of the same liquid, right? As the air pressure pushes down on the open exposed liquid, it pushes down that, so it pushes up in the tube, and as there's less pressure, it relieves some pressure on that outer side right here, and then the pressure in the tube goes down. And you can read the scale to find out what the pressure is. So at sea level, the height of the mercury in the inverted tube would be very, very high. After standardizing the mercury in the barometer, it is now measured in inches of mercury, INHG, inches of mercury, and 1 atmosphere is 29.92 inches. And this can be found in your reference table. Okay, which is going to be on page 13, and you're going to find it right here where it says pressure. All right, the other one is the aneroid barometer, which is, right here. This thing right here. Basically, it's an aneroid is a vacuum barometer. It consists of an airtight metal box with a partial vacuum to it, which means that there's that partial vacuum is right in here in that capsule. So any change to the air pressure outside moves a spring, which is right here, which causes over here to move, which causes this to move, which causes that to move. So it definitely turns a lot of stuff. So the spring moves a lever, which turns a chain, which moves the needle to indicate the pressure. So it moves all, the spring moves this, which moves this, which moves this. These are usually in millibars, MB, as the unit, but it may also have the equivalency scale of inches in mercury. Typically, we look at millimeters. So you're going to see, let me move me over here. Right here, again, on page 13, 2 scales. We have the millibars in inches of mercury. So 1 atmosphere equals 1013.2 millibars and 29.92 inches of mercury. Now, if we were to look at this and do a conversion, I would look for, the first one is 997 millibars. I'm going to come over here to 9, 92, 96, 97. Each one of these lines are worth 1. And then I'm going to go across, and I'm going to get roughly 29.44. So there's 29. There's 29.4, 29.5. Each one of these are worth 0.01. So it's going to go up to about 0.44. All right, well, let's look at this side. I've got 30.15. There's 30.10. 30.15 is this line right there. And I'm just going to follow it across to give me 10.21. All right, let's look at 10.06. There's 4, 5, 6. Follow it straight over, and I believe it's 29.71. Right on there. All right, let's look for 29 even right here, and I'm going to follow it across to right here, and I'm going to get 982. Yep. Let's go 2 straight at 1,000. I'm going to follow it across, 29.53 roughly. That one would have been like 5.3, 5.4. I could have accepted both. All right, let's look at 30.21. It's that little line right there. Go across. It pretty much makes it to 10.23. 10.19. 6, 7, 8, 19. Go across right underneath 30.10. So it'll be 30.09. There you go. All right, so that is it for the notes. If you have any questions, please don't hesitate to ask, and I hope you guys have a great day.